So what are you guys?
We are the Smartwood family! Hell yeah!
Hey guys, so we've been having some problems uploading stuff from our main, camera. So I guess the best thing to do now, since I know time is running short and you guys are about to have your final exam, is to go ahead and look at this in terms of, using the iPhone. And it's going to be a little gimpy because I'm going to have to hold the iPhone with one hand and then try to write with the other. But yeah, hopefully this will be good enough. So the last thing we have yet to do is central limit theorem, right? But what I call the reverse version. So if you look at this, it says, how many times must you flip a coin to be, it should say at least 95% certain that your estimate of the probability of getting a heads is within 0.01 of its true value. Okay, so take a second to pause the video if you need to look at this. Okay, so let's talk about what this means. Well, first of all, it means, how do you normally do this? If you're sitting there trying to figure out what's the probability of getting a heads, and let's say we don't know, then you just flip a coin, right? So if I flip the coin one time, right, and I get a heads, then I would say, what's the probability of getting a heads? It would be 1 heads out of 1 flip. Sorry, this pen's not writing. There we go. So that would tell me it's 100%. Obviously, that'd be wrong, but that would be our best guess, right? So then we try it again. Let's say we flipped and got 2 heads. Then what's the probability, I think, of getting a heads? Well, it would be 2 heads out of 2 tries, so it would be 100%. Does everybody see this is my estimate of getting a heads, right? Or the probability of getting a heads based on my little experiment here. So let's say we tried again, and this time we got heads, heads, tails. Okay, well you know the real probability supposedly is a half, right? But here we got what? 1, 1, and then a miss. So I guess it would be 2 heads out of 3 tries. So I would think the probability of getting a heads is something like 2/3. Okay, so now the question is, how do we translate this statement up here into symbols, right? So, okay, how many times must you flip a coin, right, to be at least 95% certain? Sounds like a probability. So I think I'm going to write it like this. So I want the probability that whatever we're looking at is going to be at least 95%. Okay, at least 95% certain of what? At least 95% certain that your estimate of the probability of getting a heads. So how did you do that? You did this little experiment, right? So what was our procedure? We can think of it like this. To each flip, you assign a number, either 1 or 0, basically a random variable. If you get a heads, we'll assign it a 1, so 1, 1. If you get a tails, you assign it a 0, and you add them up. And that would count 2, which would give you a number of heads, right? Okay, do you remember in the review, we call this S sub n? Okay, but that's not the way we did it. S sub n is only the top, right? It's 2 heads. So how did we get the probability? It's 2 successes out of 3 tries, so it should be this guy divided by the total number. Again, we saw this in the review. We called this thing x bar n. Okay, so now let's come back here. So you want the probability that your estimate, which is x bar n, right, of the probability of getting a heads is within 0.01. So let's look at that. Let me see if I can get better focus here. Is within 0.01 of its true value. So the true value we're going to call p, probability of getting heads. Okay, so you want that within, what, 0.01 of its true value. Okay, so I want that within 0.01 of its true value. Is everybody okay with that? Okay, so we just said within 0.01 of its true value, but I didn't care if it was higher or lower, right? So we're going to take the absolute value. This should look kind of familiar. Do you remember from the review we did Chevyshev's? This looks very similar to Chevyshev's, but it's not quite Chevyshev's. If we did this with the Chevyshev's approach, which you saw in the review video, you'd have to flip this guy around, right? Since we're going to try this with the central limit theorem, you don't actually have to flip it around. Okay. But let's see what we want. So we want this setup, right? And I want to do this with the central limit theorem. Okay, first thing is, do you remember from the review, you had some variable, I think we called it S sub n, right? Counting number of heads. And we turned this into a random variable. And we did that by saying what? Remember, it was your score minus the mean divided by what was basically the standard deviation. And I'll call that standard deviation of the individual. So you guys remember that? Okay, so what I'm going to do now is, because it's more convenient, do you agree it's the same guy if you divide top and bottom by n. So if you divide Sn by n, you get exactly what we wanted here, right? So let me move that. Okay, so you get the average, right? So this guy would be x bar sub n. Okay, and if you divide np by n, it's clear you get p. Okay, now I'm going to divide this guy, square root of n sigma squared by n. But what I'm really doing is I'm dividing it by n, but n I'm going to place underneath the square root. So do you guys agree that if I divide by n squared, that's the same as dividing by n, because the square root of n squared is just n. If you do that, you're going to get this thing here. And so now let me rewrite this. This guy is x bar sub n minus p over, I think it looks like, well, the square root of sigma squared is just sigma. And then what we have left over is 1 over the square root of n. And you know, since it's 1 over this guy and he's on bottom, I can flip him up to the top, right? So finally we're going to get this guy, square root of n, x bar n minus n over, minus p over sigma. Okay, that's our guy. So this guy is that wannabe z-score. The only difference is I divided the top and bottom by n. That doesn't change anything. So why the hell do I want to use this? It's because of this. Remember, the question is solve for the number of coin flips, right? I need that n in there so I can solve for it. Okay, so let's go back. Okay, so what's the probability that your estimate, right, of the probability of getting a heads is within 0.01 of its true value? And I don't care about the direction, so I use absolute value, right? And I want to be at least 95% certain. So this is our statement. Now we're going to take this guy and we're going to convert it to the wannabe z-score. Okay? But before we convert it to the wannabe z-score, let's get rid of that absolute value. So you guys remember, if I had something like the absolute value of x is less than, say, 100, how can that happen? Well, one way is x is definitely less than 100. I think that's obvious, right? But another way is, what if I had this x being negative 2 million? Negative 2 million, the absolute value would be 2 million, and that's definitely not less than 100, right? But if I had, say, negative 90, the absolute value of negative 90 is what? 90? So 90 would be less than 100. So actually, just to save time, you can go both ways, right? So you need a guy that's could be negative, but not more negative than negative 100, and he could be positive, but definitely less than 100. Any one of those, if you think about it for a sec, will give you an absolute value less than 100. So that's what we're going to do. We're going to kill this guy. So we're going to rewrite this like, that would be the probability that xn bar minus p has got to be less than 0.01, right? But also greater than negative 0.01. Okay? So that's what we're looking at. Okay. So now, and of course I don't want to write it, but on the right hand side it's still greater than 0.95. Okay, so what do we do with this? I want to turn this into my wannabe z-score. So we just do that. It's almost in the perfect form, right? X bar n minus p over sigma, and don't forget that square root of n, right? Okay, so I just write this guy like this. But remember, we have to line everything up. Do you remember last time we did the central limit theorem? The number you add here corresponded with Sn. This is different though. 0.01 corresponds to x bar sub n minus p, the whole thing. So wherever you see this guy, you need to plug in 0.01. So you go over here and do this. So let's plug in for the upper region. That's going to be root n, right? Let me pan back here. And that's going to be 0.01 for the entire guy up top, divided by sigma. And I come over here and do exactly the same thing. So it's square root of n, right? But now negative 0.01, because I have a negative over here, right? Divided by sigma. And I take this whole thing, and we're looking at the probability of that guy. I just rewrote the statement, right? Sorry. Translating that top guy into the bottom guy. And I want this to be what? Still greater than or equal to 0.95. Okay. So that's our statement right there. Now remember the step here. This looks like a wannabe z-score. Let's take it to an actual z-score. So by the central limit theorem, you can just pretend this is a big fat z. Okay? Then I get square root of n 0.01 over sigma. On this side, I get square root of n negative 0.01 over sigma. And I get the probability of that. Okay? And all of this is greater than 0.95. Let me pan back so you can see that. That's what the central limit theorem lets you do. Okay, so now what? Do you remember that trick we talked about at the very end of the review? Since we're talking in terms of z-scores now, you've got this z-score, right? And you've got that z-score. And you see how they're related? This is the positive version, and this is exactly the same number, but it's the negative version. Do you guys agree? So if you can do that, do you remember our trick? If you had a guy, let me first write it over here. Well, it looks horrible, but you get the idea. Pretend it's symmetric. If you have a guy like this, and you want the region in between, do you remember our little trick? It was 2f of the upper z-score minus 1. So look back at your review notes, and you'll see this, right? Okay, let's come back and do the same thing. Pick the upper guy. So 2f of the upper z-score, which is square root of n 0.01 over sigma, this guy, minus 1, is going to be greater than or equal to 0.95. Okay, so now it's a little. We're going to do a little thinking in here, but first let's do some arithmetic. Add 1 to both sides. So this is greater than or equal to, 1.95. And then over here, how would you get rid of that stupid 2? Well, these are just numbers at this point, right? So we're going to divide both sides by 2. So we get this guy divided by 2. Okay, now the part that's going to be, it's not that bad. Let's just think about it for a sec. Normally it would be like this. You would have something like f of, say, 2. And you would go look this up in the table, because that's your z-score, right? And the table will give you something like, I'm totally making this up, I should actually know this, but let's say 0.795 or something. So you look this z-score up, and the table gives you this answer. Okay, now we're going to go backwards. Remember the backwards version? You look up the percentage in the table to get the corresponding z-score. Do you guys agree? Okay, I'm going to do that up here. So let's go back to this guy. This is now a percentage. So I look this up. Pretend it's like, what was that, a freak coincidence? I think it is. I think it's 0.9750. Okay, so this guy is 0.9750. You look at backwards in the table to find the corresponding z-score. I don't know what that is. Thought hard enough, maybe you could figure it out. Or better yet, if we use a table, get an exact answer. But pretend it's 2. Okay, so we'll just fake it. So we get some answer here, pretend it's 2. Then do you agree? Whatever answer you get from the table should be this. That's what the z-score is, right? F of something would give you greater than or equal to 0.9750. Now you're going backwards. 0.9750 goes back to f of 2. So that something and the 2 must be the same. So now we make the big jump. So square root of n, 0.01 over sigma, right? Just copying that part. It's got to be related to 2. Okay? So what we did was, we know this guy goes to 0.9750, which is this, 1.95 divided by 2. We know if we go backwards in the table, we get 2. It's not really 2, but just pretend. So we know these two numbers must be the same. So this guy must be related to that, right? I'm going to do one more quick tweak, just in case the prof is anal. Since you want a z-score that gives you this number or bigger, the z-score we want is going to be 2 or possibly bigger. So I'm going to just put that in there. Bigger. Okay. Now it's almost arithmetic. You can solve for that square root of n, but the problem is solving for that square root of n, I need to know what sigma is. But that too we talked about in the review. So you remember, for this binomial guy, how do you get sigma? Sigma is going to be, it's the square root of the standard of the variance, right? And the variance was what? N times p times 1 minus p. Two ways to remember this. One is, remember how I always talked about this sigma being sigma of the individual? Well, if that's true, then n would be what? 1. So it's the square root of p times 1 minus p. You saw us do that earlier. For flipping a coin, p is a half. So 1 minus p is a half, and a half times a half has got to be a quarter, right? So the square root of a quarter is a half. Okay, so this mess down here is going to be square root of n times 0.01 over, I think, a half. Okay. Should always double check my arithmetic. And then it's still going to be greater than or equal to 2. So from here, you could totally solve, right? I would multiply, what, both sides by a half. So I get this to be 1, right? I would divide both sides by 0.01. So that would add 2 zeros here. And I would square both sides. So in this case, my answer, I get 10000, 10,000. This is probably not the right answer because, 0.9750 doesn't really correspond to 2. I just guessed, made a guesstimate here. But the procedure is totally correct. So if you use a table, you get the exact answer. Okay? So I know that was kind of painful. Let's go through this one more time, and I'll try to talk you through it. Okay? So we start off with the same thing. We translate this in the symbols. So how many times must you flip a coin to be at least 95% certain that your estimate of the probability of getting a heads is within 0.1 of its true value? So what are you looking for? You're looking for n. So never forget that. You're actually looking for n. Okay? Okay. Now let's go back. Let's translate this in the symbols. So you want us to be at least 95% certain. So at least 95% certain is a probability, right? So this probability, so 95% or greater. Probability of what? That your estimate is within 0.01 of the true value, which we'll call p. Absolute values, because I don't care if you're above or below, I just care that you're within the range. Okay. Second, turn it into a wannabe z-score. It'll always work out this way. We're going to push it, we're going to skip all the way down to this guy. X bar n minus p over sigma, that looks very much like a z-score, and that n that was there before is over here, so root n. Okay? Now I kind of know I'm on the right track. Why? Because if you look at this guy, right, you're going to solve for n. If you don't translate, there's really no n up there to solve for. So down here, you can definitely see that. Does everybody agree? Okay, so now I got 0.01, I've got that sigma, I've got that square root of n. Now look at that square root of n, try to solve for n. But first I plug everything in. So, you know, on the upper end, 0.01 goes for x bar n minus p, so that's going to be over here. You know, on this end, you have negative 0.01 for x bar n minus p. So x bar n minus p becomes negative 0.01. You have this setup. You notice this is a z-score above and a z-score below, and they're symmetric, so you can do our trick. So what was that? That was, I have it here, 2f of the upper z-score minus 1. Still greater than or equal to 0.95, right? We do a little bit of stupid arithmetic, and then we get it down to f of square root of n, 0.01 over sigma, greater than or equal to this guy, which is 0.9750. Okay, the only thing now is I have to go backwards in the table. It's not really 2, but we faked it and said it was 2. That means this guy and 2 must be the same. So I should set up an equality. But if you look at the left-hand side, I wanted my guy to be at least this or bigger, so I want my z-score to be at least 2 or maybe bigger. Okay, then some more stupid arithmetic. Don't forget that that sigma for the individual, at least for binomial, right, is going to be p times 1 minus p, take the square root. Okay, and then we're going to get down to here, more dumb arithmetic, and then we're done. I don't know if I mentioned this during the review, so rule of thumb, you really only use it for this case when you're estimating sample size. Rule of thumb is, what if you don't know p? I mean, because it's in real life, but it might also occur on the exam, it's kind of stupid to assume that you know p is a half, because if you did that, then why the hell are you trying to estimate the probability of getting a heads, right? So the thinking is, if you don't know what the value of p is, because you're trying to figure it out maybe, right, you always assume it's a half. The reason why you assume it's a half, this is like a bad trip back to Math 3A, I think, or something. If you look at this guy, I won't do the details, but if you look at this guy, he's an inverted parabola. So he looks kind of like this. And if you want to be safe, you always estimate for the largest error, right? The largest error, where's this function going to take the largest value? It's going to be right here. So if you took that function, which is, I think, negative p squared minus p, right? Isn't that, where is it? P times 1 minus p, that's going to be p minus p squared. So minus p squared plus p, sorry. There we go. Okay, so if you look at this guy, right, and you actually map him out, you can take the derivative, set it equal to 0 to find if it's a max or min. You can take the second derivative, and it's pretty easy to see, just even pictorially, that this guy up here, he's going to be a max. And he takes the max value, actually, at p equal to a half. Okay? Okay, so hopefully this helped. If you guys have any questions, we're going to be up pretty late, so just email back anytime. And good luck on the final.